20 grand.
20 grand.
Once. Still got some cherry kick flavored root Lucozade in it. I'll throw that in for free. Anyone buy any NFTs recently?
Oh, nice.
Yeah, I right click and saved as so many times.
NFT's worst nightmare is copy and paste. Save image
I
apps.
saw people buying them. I just like, but like, why did
Well, it's just
Because
to actually make art.
the idea is it's money laundering. Basically.
Yeah, that's all it is.
Like you're paying money to own it. You don't own the picture. You own the link for the picture, like the website. The picture is on.
If you're doing money laundering, you should take into account I'm recording down the thing, okay?
I'm not doing it. Don't worry. I'm not money laundering.
You know, I can edit it
As far
later.
as the recording is away.
I didn't. Well, I heard. Okay, right.
I just want to be ocean.
One,
someone.
someone great.
One
for the ocean buddies or something.
Oh, what a pencil case. I love it. I'll be your ocean buddy.
I gave you. Did I give you last time some printout pages?
You did.
What's on the other side of that one? Oh, okay, graphs.
Oh,
God.
This is someday my third year project, so I needed a reminder. Wow.
Or it's the stuff from last time.
Okay, so a quick reminder, the point where we stopped last time. Okay, can I start? Last time we were looking at this schematic diagram. You don't have to draw it because you should have it in your notes, where we had some pump, and we were looking at various processes which were producing gas, and as opposed to the only process which is extracting the gas, which is the pump. Okay, and the idea was to try to understand how vacuum is achieved, and this is going to lead us today. What we're going to be talking about is we're going to be starting to talk about different types of pumps, which you might encounter in the lab, and how they work and so on. But the main idea I wanted to kind of convey is that even if the pump was ideal, so it would be pumping a certain amount of molecules per second, you know, forever, you could rely on it, it would never empty the vessel out of gas. And that's because we have processes which are producing it. We had some of these that were maybe avoidable, like leaks. That would one example which we thought about. And we have a contamination, right? I don't remember exactly how I phrased it. It could have been something like that, but it would be all kinds of liquids, you know, grease, whatever, there's stuff on the. But there would be also evaporation of the vessel, if you want. Or the materials which are inside that chamber. And this leaks is pretty avoidable. Contamination only to a certain degree, and evaporation of the vessel, you can't fight it because you always have a vessel. Okay, and we had a pump extracting, and then there would be some kind of equilibrium when the amount of molecules being produced was equal to the amount of molecules being extracted, and that's where the thing would stabilize, and that's the pressure we'd have. Because the pressure is a characteristic of the number of molecules inside the chamber. And we can always remind ourselves of this PV equals NKT, which tells us that as long as the temperature is the same and the volume is the same, the pressure is simply proportional to N, the number of molecules in the chamber. Or if you want to write it with nRT, it would be the number of moles. Okay, same thing. So we'd never get to a situation where we're running out of molecules. And I want, before we continue, especially because a lot of you are doing organic related research, I want to talk a little bit about this evaporation and contamination. And in order to do that, I want to discuss the concept of vapor pressure, which is something you've learned about, but then again maybe forgot. So could you look at these pages I printed out for you last time, and Sam, if you don't have them, if you could just look together with. Okay. So does everyone have that thing, or look at one next? That's fine. So on one of the sides, don't look at the one with the. Let's start with the one with the phase diagram of water in its liquid, solid, and vapor states. Okay, so can you see that diagram? That looks familiar, probably from GCSE, and then again in A level, then again a little bit in the university and all that. So you've encountered that. So on this, what are the lines on this diagram? Let's remind ourselves. Thick black lines there.
They're like the boundaries, isn't it?
They're the boundaries. Okay, so they represent an equilibrium between two phases, right? If you're sitting on the boundary, and sitting on the boundary would be a particular pressure, which is the vertical scale, and a particular temperature, which is the horizontal scale. So if you park on one of these boundaries by choosing an appropriate temperature and pressure, you're at equilibrium. What does this mean? Does it mean that water stops freezing or that ice stops melting?
It means they go at the same rate.
Yeah, so exactly. It's what's called a dynamical equilibrium. This means the processes happen all the time. Water is freezing and the frozen water is melting, but the rates are equal. Okay, so if you look at a chunk, or if you look at the overall volume of ice in your sample and overall volume of water, they're equal. Okay. For example, if you prepare yourself in a hot day a nice glass of water with ice in it, it is not an equilibrium, and slowly the ice vanishes. If you do the same experiment at 0 degrees C, I don't know why you'd like to prepare yourself this drink, but let's say it was 0 degrees C and you'd like a nice cold glass of water, it would stay there. So the amount of ice and the amount of water would be in equilibrium. Okay, so that is all familiar, right? Now let's look at the line between the water and the vapor. So what happens at the line between the water and the vapor? It's the same thing, right? So if we think about a vessel which has some water, okay, and it has some water vapor above that liquid. So this is liquid, and this is the gas. This is what's called the water vapor. So what sitting on that line between the vapor and the liquid, what is it telling us? What's the equivalent of what I just said about the frozen phase, the solid phase? Again, sorry, whatever you're saying is probably right, so just don't be afraid. Worst case, it's wrong.
So like the liquid's becoming water vapor at the same rate the water vapor is condensing back down into a liquid?
Exactly. So we have a balance between two processes. One of them we could call evaporation, okay, and the other one is condensation, right? I think this would probably be the terms you condensation. Okay. So you have a balance. They are both happening, as you said correctly. They're not stopping. All the time, water molecules are leaving the liquid. All the time, water molecules are being condensed onto it from the gas phase. And if you look at the sample for a long time, it will be in equilibrium. At some point, there will be no loss of water. Whatever the liquid is, it's going to stop there, and the gas and it's going to stay there forever as long as I close the lid on this vessel. Yeah, do you agree with me? That's kind of your life experience. So far, so good. So what does the term water vapor mean? Vapor pressure. Water vapor pressure mean in this context? How does?
Isn't it the space in between, like just above the surface?
So you're saying that there's this kind of area just above the surface. What's special about this area? Right. Back there. Yeah. Have you heard the term vapor pressure before? You've heard it.
Yeah.
Come on, try to use the things you do know about it to answer my question. It could be not about water. It could be about solvents. It could be about whatever.
This is just the pressure of the gas pushing it back down or something.
Right. So it's the pressure of the gas.
vapor.
So what you're saying is that it's the pressure of the gas. So this would be the pressure, what's called vapor pressure. Or sometimes it symbolizes PVAP. That sometimes is the way to write vapor pressure, which is pushing back. What do you mean by pushing back? Was it like an argument? Why is it pushing back? Why can't it just accept that liquid is liquid?
All the molecules like hitting into the water as well, right?
Right. That's now we in the if you guys weren't in my lesson last week, I'd say, great, let's stop there. But you were in my lesson last week. So let's try to think about things we learned last week. How does that tie up into the pressure? What happens when you have a vessel and you put some surface, in this case, it's the surface of the liquid, but it's still a surface. What happens when you have a pressure of gas above it? What happens to the surface? Does it know about the gas? Does it interact with the gas? Does this window interact with the gas in this room?
Yeah.
Yeah.
In what way does it interact?
It's constantly.
It's constantly hitting the wall, right? Okay. What about the liquid water? What about the water in the gas phase? It's all the time hitting the water, right? So it's hitting the water, but the water is not like this. The water, there's a water attraction. So if it hits the water, there's a good chance it's going to stick to it, right? Let's say it's a 100% chance. Okay. So now let's connect the different terms we've learned. So we have this vapor pressure basically means that we have some kind of impingement. Remember this concept, impingement rate? Someone remember what the equation was for this impingement rate? By chance of writing it on the board correctly without
G to the quarter and.
yeah.
Oh, well, we doing that one.
Yeah,
Yeah,
the other one.
Yeah, the other one. 2 pi PV T.
In a square root, right? Something like that, right? So for any pressure, there is an impingement rate. In this room right now, there's huge impingement rate of molecules on the walls. If I pump it down, we'll all die. But before we die, there'll be less and less molecules hitting the glass, right? How much less? Well, linearly with P. So if I take the pressure down to half the number. If I take it by 6 orders of magnitude, 6 orders of magnitude down. Okay, so it's linear with pressure. It's a bit more complicated relation to temperature. Remember that was to do with how fast they're hitting it and therefore how much force they're transferring the molecules and so on, but let's leave that for a minute. We have this equation. Now, you could put any pressure here and get an impingement rate. But what does this diagram tell us? If we look back at the diagram, it tells us there are particular pressures where you have equilibrium. Okay, so where the number of molecules leaving the liquid phase is equal to the ones hitting it. Okay, do we agree? So it means if I park on that particular pressure, if this is not any pressure, but if, let's say, if P equals P VAP, so if the pressure I choose is P VAP, okay, then basically I have the impingement flux is equal to the evaporation flux. If I'm writing flux to not be bothered with the area. So it's an expression which you can then multiply by area and get the actual number of molecules per second, but I don't care. Okay, it's the same area which is evaporating, the same area which is receiving the molecules. So I don't really care. Does that make sense? So using that understanding, could you, and using also the table that you have in your in this page I printed out for you, tell me what you'd expect in equilibrium. What would be the pressure at, let's say, 2 temperatures, at room temperature, which is about 300 Kelvin, and maybe at 20 degrees, minus 20 degrees, okay, a bit chilly. So have a look at these tables. I don't know if they actually cover room temperature, do they?
Yeah.
They know they go up to 0 degrees C, right? Or is there also one?
Oh, there's the vapor pressure one on the right as well. There's to 100 degrees.
Where's that? Okay, you have it. Okay, perfect.
Yeah.
Okay, so could you try to excellent. So could you try to tell me, just look at these things and tell me what you think the relevant pressures will be.
About 3.17 at room temperature in kilopascals.
Which one?
So here is 3.17 kilopascals at 25 degrees C, which is about, well, it's not too many.
Sorry, that's what we're looking now at room temperature? Yeah, so that,
Yeah,
that's,
yeah.
sorry, which one are we looking at? 300 Kelvin?
Yeah, 300 Kelvin is like sort of 25 degrees of it.
Yeah, roughly, so that's about 30 millibars, right? About 0.03 of an atmosphere, sorry, okay? Does everyone see that, those numbers, okay?
Yeah.
So I think this one, at the 300 Kelvin, we're talking about, you could use various different units, but we're talking about more or less 0.03 of an atmosphere, which is, atmosphere is like a bar, so that would be 13 millibar, because it's 0.03, 0.003 would be 1 millibar. Anyway, you could do these at your own rate, but this is roughly 0.03 atmosphere. What about the minus 21? Let's maybe, we might need some unit conversion, because of course the tables won't be consistent.
Yeah, so this one's 1,000 microbars.
Yeah, what a nuisance. Okay, so what's the relation between a microbar and a millibar?
Is it just 10 to the 3?
10 to the 3, right? So we have micro is 1 over a million, milli is 1 over 1,000. So that would be, or that would be, how much did you say it's microbar? Sorry, how much?
It's 1,032 exactly.
So it's more or less a millibar, right?
Yeah.
Okay. So we're talking here on the order, and a bar is like an atmosphere more or less. Okay, I'm very crude with these things. I don't care about. So we're talking about roughly 0.01 of an atmosphere, I believe. No, sorry, 0.001. So that's 1 millibar, right? So it's quite a dramatic difference. So we went from, by the way, are we all here? So which means I don't need to record. 2, 3, 4, 5, 6, 7, 8, 9, 10, right? One missing?
Patrick's missing.
He's in the lab still.
You're 11.
There's 11 of us.
Yeah. Okay. Are you sure you're not 10? Okay. I was told you're 10. Okay, so we'll keep the recording for Patrick. Okay. So what did we discover? We discovered that if we had this if we took this vessel and we somehow wanted it to be in equilibrium, so we left it on its own, you'd have initially, maybe it would be out of equilibrium, maybe you'd have more evaporation, maybe you'd have more condensation. But after a while, if you kept it at this temperature, the pressure above would be 0.001 of an atmosphere. What would happen if it would be higher? The pressure of water, okay, water vapor. What would happen if the pressure would be higher? Well, you look at this diagram that we have there. Okay, so let's look at the diagram and look at the boundary between the water vapor and water. Okay, so increasing the pressure means that we're no longer at the boundary, right? We're going, so if we increase the pressure, that's going up on this diagram. It means we're going from the interface between the vapor and the liquid into the liquid. So what does that mean about the balance between evaporation and condensation? If we're now in the water part of the phase diagram, what does the water want to be? It wants to be liquid, right?
So favoring condensation.
So you're going to have more condensation than evaporation, which will what's going to happen to the pressure as that happens? You're taking away gas phase molecules. So you have less and less molecules in the gas phase because you have more and more condensation. So what does PV NKT tell you about the pressure? You have less and less molecules. The pressure will drop. Where will it stop dropping? So you're gonna have more and more and more water, more and more liquid water, sorry, until the pressure drops to the vapor pressure. Once it's at the vapor pressure, it's equal again, okay? So you might end up having, if you start by filling it with water, which is at a pressure which is higher than the condensation pressure, you're going to have more liquid, okay? But then after a while, it's going to stabilize, and that's it. If I would do the other thing, if I would extract, let's say I would pump on this thing. So imagine that I'm connecting this guy here to a pump, just pumping. What happens? Let's say this is a pump, which is, a great pump. It achieves zero pressure. Whatever comes out you go, okay? How many molecules do you have in the gas phase? Well, essentially nothing, because whatever evaporates is quickly taken away, okay? So what happens to this balance between the vapor and the liquid? It's out of balance, right? Because there's nothing to resupply the liquid with molecules. The evaporation is happening at the same rate. It doesn't change. The reason for evaporation is if you want thermodynamics. There's some heat there, bonds are broken, things happen, water evaporates, but there's nothing to correct for that because there's no gas to absorb. Do we agree on that? The impingement rate, which we talked about earlier, is 0 because we're evacuating. The P is less than P vac, okay? So what's going to happen to this liquid with time? We're just pumping on it. We're going to get less and less and less and less because the evaporation is happening at the same rate. Condensation is not happening, okay? And we're losing. And then again, if I would suddenly shut the valve of the pump, what's going to happen? Could you say again, sorry?
Vapor pressure is going to go back on.
So the vapor pressure is what it is from the table. The pressure is going to go up onto the vapor pressure and park there. Okay, so this is what happens. If this thing was not water, but it was one of your nasty solvents, it would probably happen at a different pressure. Okay, because it's given by a different table. The equilibrium between evaporation and condensation is at a different point. For example, if you know that if you squirt some I don't know, alcohol on your table and some water, you know that one of them is going to evaporate before the other, right? Has a higher vapor pressure. If it has a higher vapor pressure, it means you need to put more gas on top of it in order to achieve equilibrium. Okay, that's so whenever you try to think, is it higher vapor pressure or lower? You know, what's am I going to lose my solvent before? Am I going to lose solvent A before solvent B? The meaning of higher vapor pressure means you need a higher pressure above it to stabilize. You need a higher impingement rate. Okay, so that's really not to do with vacuum so much. It's to do with vacuum, but it's also to do with chemistry. So this is like, I think, worth knowing. Okay, you probably had all the ingredients to know it, but hopefully it will sit a bit better in your heads now. Okay, so now let's look at. So why did I mention this? I mentioned this because you remember when we closed the chamber, we were speaking to a friend and we were spitting a little bit while doing it, as people do, and we had some water in our chamber, which means that we're going to have a pressure here. We can pump it, but all the time water molecules are being evaporated, okay? And as long as there is liquid water here, the system will kind of tend towards vapor pressure, okay? But luckily, with time, we're going to deplete these water molecules. And if we have time, I'll give you an exercise where we could actually calculate that depletion rate. And the answer is we can. Okay, you can. Okay. And if we have time again, we'll do it. But with time, you understand intuitively that you're going to have less and less of these water droplets until they all evaporate. And when they all evaporate, if that ever happens, your pressure will be able to go below the vapor pressure of water. Before that, it was always stuck to that level. Does that make sense? Good. So indeed, what people do is they clean their vacuum chambers. They try not to spit. They try not to, use oily fingers. So they work with gloves. You'll see people working on vacuum chambers typically try to work with gloves, not to protect themselves, but to protect the chamber from their lunch residue, which is still on their fingers, which will take a long time to pump away. Okay, so that's why people work clean. But nevertheless, there's always going to be some contamination. And we'll talk about ways of maybe getting that, if we'll have time, away. But now let's talk about the evaporation of the vessel. Could you look at the other side of this page, where I think, if I'm not mistaken, let's see. Yeah, there are two graphs. And no, this is not an eye test. So you should be able to well, I can't, but you can because you're young and all that. So the units on the vertical scale of the plastic material graph, sorry for stealing yours, goes from 10 to the minus 3. Maybe you could write on that. So what's written there is 10 to the minus 3 of these units, which are millimeter of mercury, 10 to the minus 4, 10 to the minus 5, 6, 7, and 8. Okay, could you just about see that? So maybe just write that so it doesn't become a. So it starts from 10 to the minus 3. Okay. Okay. Now let's start by looking at the plastics. So we like building everything from plastics. It's very cheap, very light. It could be transparent. It's great stuff, really. Let's think about it as a vacuum vessel, if it's a great idea or not. Now, these graphs, have you ever seen graphs which have a horizontal scale similar to what's on these pages?
And what, like,
The horizontal scale. Let's start with the horizontal, the X scale. What's written there? It is in English, right?
1,000.
So is it 1,000? And then what's written?
1,000 over
over
T.
T, but it
Kelvin.
And Kelvin. Okay. So what that means, and you could get used to that maybe one day. And it's used for all kinds of activated processes. And if you want, I can explain that. That's kind of physical chemistry. But just sticking to these funny units, what this means is that whatever number you're seeing there, you should divide 1,000 by that number, and you're going to get your answer in Kelvin. Okay. So let's see where's room.
So it's 500 degrees on the left, basically.
So the left is 500 degrees. What's the right?
It's 3.8, so that's going to be like
Let's do the maths.
263 Kelvin.
263. So it basically, first of all, these are kind of, it's a funny way of drawing it, because essentially what you have here to the right is 263. So you have a higher temperature to the left, right? So it's about 500, you said?
Yeah, 500.
500. Okay. So, and what are the values at about room temperature? So we can always check what room temperature is, right? So if we take 1,000, divide that by 300, we're going to be at 3.3, right? So it means that have a look where 3.3 position is, and tell me what's the Y value there for some of the plastics. I mean, there are various plastics in this graph. And which ones are on there? So we have. Are there some? Do you know some of these guys?
Teflon, vinyl, nylon, cloth, butyl rubber.
Okay, so you could see the ones. So at this 3.3 value, there's a huge difference between them. Some of them are already in 10 to the minus 3. So 7 and 8. Is that right?
Yeah, 7 and 8 here.
7 and 8 are already 10 to the minus 3 torrs. Okay, torr is more or less like a millibar. So 0.7 of a millibar. So you have these tables. So that's extremely high vapor pressure. Okay, so it means, well, extremely high. It's much lower than an atmosphere. It's about 1/1,000 of an atmosphere, but it's still very, very high with respect to the different regimes of vacuum, et cetera. So if we're going to use a vacuum vessel made out of whatever material that was, it's a horrible idea. Okay, it means that if you have very high vapor pressure, first of all, you'll never be able to achieve a low enough vacuum, because all the time your vessel is evaporating. And if you're going to leave your vessel like that for years, your vessel is going to disappear. Okay. Now this sounds like a bit of a strange situation, but if you're I don't know, if you're on the building material for the space station, okay, which is in vacuum essentially, you don't want the bits to keep evaporating, and you don't want to lose your windows, right? So you're going to choose maybe glass rather than some kind of polymer. Okay. So vapor pressure is all about stability, and we could see that it range. Some of these guys are better, some of these guys are worse, but all of them have vapor pressure which is not negligible. Okay, so which means that you need to supply the material in gas form if you want to stabilize it, which is bad news for vacuum. Okay, does that make sense? The higher the vapor pressure, the worse it is for vacuum, especially if you heat these guys up. Now, the reason these plots are done in this funny unit is, I mean, you've seen many times in chemistry, we have some process, and that process happens as delta E over KT, right? You're familiar with that. So this is where the incentive comes from 1/T. The 1/T, the reason these graphs are done on 1/T, these are called activated processes, right? Have you heard the term that you have some activation energy to go over them? So when you have anything which looks like e to the minus delta E over KT, it's worth plotting it. You do a log of that, you get rid of the exponent, and then you plot it as function of 1/T, and it becomes linear. Okay, that's the reason. I don't know if you've never encountered that. You did that in A level, okay, but then not in university, right? It's kind of strange.
It was kind of like we drew graphs where we'd have
Yeah,
like
we did.
1/T.
You've seen
you'd
that.
have like a gradient, 1/T,
Okay.
y descent and stuff.
Okay, good. I'm relieved to hear that you've seen that.
Yeah.
So could we just look at the other scale there? So that's a bit of an again, I'm doing it not so much for this course, but this to kind of keep you guys in shape. So the x-axis is the same irritating x-axis. I think it's right. It's 1,000 over t.
10 to the
Or
4.
10 to the 10,000 over t, just to be annoying. Okay. And then the y scale is the logarithmic of the pressure. So what does that mean? So if I want to know what the pressure is, what do I need to
You
do?
need to do e to the power.
Yeah,
Wait,
so
no, it's
it could
not.
be
It's
either
a
10 to the
natural
power.
one, it's not natural.
Exactly, it's probably
It's base.
it's base 10. I would guess. Okay.
Yeah, I assume
So you'd have to do 10 to that power, and minus that would be the pressure. Again, I'll give you some exercises if you want. I don't want to waste all the time on that, but the bottom line is that that graph is for what? For aluminum or something? Copper. The answer is copper sounds like a material which you're not going to worry about it evaporating. And if you look at that graph and you do the exercise, which maybe I'll give you, or maybe just give you just an exam or whatever, okay? But it's just about putting in numbers. You'll see that if you heat up copper to 1,000 Kelvin or maybe 1,500 Kelvin, then you're starting to have a problem. Okay, so you're starting to have a vapor pressure which is noticeable. Now that sounds maybe bizarre, but sometimes you do very high temperature chemistry, right? Sometimes you want to burn something. Okay, if you want to burn it, you want to melt it, it's evaporating. How fast is it evaporating? Maybe before you couldn't answer it, but now you can answer it. Because whenever someone asks you, how fast is something evaporating? You know, because you know what to do with vapor pressure. You put the vapor pressure in the impingement rate equation, and you could work it out in molecules per second per unit area, okay? Because that would be the pressure which would be required to balance that evaporation, okay? And again, if we have time, we'll do some exercises. But if not, let me just try to summarize a few of these points we talked about, okay? Maybe I'll write that down. Is there a place right here? So maybe the kind of important messages are that the vapor pressure, it basically marks the balance between evaporation and condensation. And maybe it's worth mentioning that condensation can be either to the liquid or to the solid state. Okay, it doesn't matter. If you look at that graph of water, at some range of pressures, ice is going to go directly into vapor. It's not going to go through liquid. If you do low temperature experiments, your ice is going to evaporate. It's never going to go through water. Okay, but it doesn't matter. The vapor pressure is a concept which works for any condensed, that means solid or liquid, phase versus gas. Okay, is that known, right? A second thing about, or basically, if you want, coming out from that is that impingement rates basically impingement rates allow us to calculate evaporation rates. Okay, that's assuming that P vapor is known. I'm going to need to replace this. And then I'll just mention that basically vacuum components are chosen to have low enough vapor pressure. And I'm writing that it's at the relevant temperature. Vapor pressure is always a function of temperature, and it changes a lot. We saw that just for example of ice, it changed by a factor of 30 by just cooling it down by 20 degrees C. Not much. It's a huge, huge change. It also means you could work with horrible materials as long as you keep them cold enough. have an ice chamber. An ice chamber. That's really cool. By the way. Nice to have. I'll just mention that this basically another point here is that the concept of vapor pressure can be extended to adsorb layers. And I'll explain what I mean. What I mean by that is that if we have a surface of a material or whatever, and we put some contamination molecule on top of it. Let's say this is my contamination molecule. It looks like water, maybe. The amount of absorbed water onto that surface also introduces a concept of water, some kind of a vapor pressure. So there would be some, so to have, let's say, half of my surface covered with water molecules, there'd be a certain rate of impingement, which would be equal to the rate of evaporation, okay? So while the diagrams you've seen all your life are always for a solid material, so it would be just ice or just copper or just whatever, you could also think of combinations of a contaminant on top of a surface, and it would also have, without going into the details, there will be some kind of balance. If these guys are leaving the surface once in a while, if I supply them at the same rate, I'm going to keep the amount of contamination constant. Okay, so it's very similar to the concept of vapor pressure so it also holds for adsorbed layers. And it's hard to find that in literature, but you can find sometimes values as well. Okay. So again, exercises we'll do if we have time for that. Okay. I want to now switch gears and talk about technicalities of how do you pump a chamber. And I think some of you have produced vacuum, right? In your life, some form or another. And it was involved in basically pressing a button which had an on or pump or something written on it, or was it a bit more than that? Turn a tap. Okay, so there's either pressing a button or opening a tap because there's a pump somewhere doing the work, right? Why am I bothering telling you what happens? You know, you could basically ride your car without knowing how the engine works. Who cares? You know what you're supposed to press, and it takes you from A to B. Okay, and as whether you're scientists or engineers or anything like that, you will possibly take your equipment to the limit. You want to do a new type of experiment or a new type of reaction, which is different from the other type of reaction. You want to know whether opening that valve to whatever is beyond the other side of the pump is going to work or not. Okay, so I think it's worth having some idea of how pumps work, and let's see if this is a demonstration which will unfortunately not tested, so it's probably not going to work, but it basically explains the idea. So if I have, so this is my I chose a gauge from many years ago as my vacuum vessel. So this basically has some small volume here, but it's nice enough to also show us what the pressure is. Okay, that's called the vacuum gauge. It's actually also a pressure gauge, so it goes beyond 0 when it's positive pressure, and it becomes negative number when it goes negative. And later you can have a look at this guy. And these are slightly different units, and it also moves without me doing anything, just by tapping on it. Okay, which tells you something about the age. These are called gauge units. You remember, pressure was already confusing before because we had lots and lots of conversion units. But then people, which is really irritating, they call the pressure that we live in 0. Well, some people do. That's called gauge pressure. So instead of talking about the absolute pressure, you talk about the pressure with respect to 1 atmosphere, which is where we live at. Okay, and then you could talk about negative numbers and talk about positive numbers. Why does that annoy us? It annoys us because if we know the ideal gas equation, which is PV equals NKT, what do we do with a negative number there, right? What does that even mean? Okay, so you always have to, if you want to use any of the expressions which we learned in our course, you have to convert. If you see anything which is in gauge, so someone talks about a zero pressure or zero or minus 0.2, you know, you have to add 1 atmosphere to that. Sorry, you have to add 1 atmosphere to it. Okay, so 0 becomes 1. Does that make sense, what I just said? Okay, so I want to pump this guy. How can I pump it? How do you pump gases? Come on, give me, I mean, I'm desperate. I need this gauge to somehow move, but not because I'm tapping it, but because actually the pressure is reducing.
Like a straw socket.
Oh yeah.
And it has to be carbon compatible as well. Sorry. Okay, we start without being.
Do the math.
That's very good. Okay. A mask with a small hole where COVID particles get stuck on the wings, and yeah. Okay. So I mean, let's try to. So we have this vessel here, which I'm just erased. I'm replotting, and I want to extract molecules out of it. I want to build some pump. You said to do something with a straw, right? Which was basically what, to suck on that straw, and yeah, okay, that will work. It will work to a certain degree. How does that work?
Create negative pressure on one end and it flows through from the other. Is that how
Lungs are creating a different pressure.
changing volume?
Each time we breathe, we're actually creating a little bit of vacuum. If we connect that to something, we are actually creating vacuum. Okay, so how are we breathing? What are we doing? We're expanding one volume. Okay, so if the pump, we're connected to the pump. This is our pump. Let's say this is our pump, and we're expanding the volume of the pump. Okay, what happens if we expand the volume? If we think about the ideal gas law, for the same temperature, the same number of molecules or moles, same Boltzmann factor, what happens to the pressure if we increase the volume? Pressure decreases 1/, right? I double the volume, I have the pressure, right? Because easy equation. So how do the molecules here? Okay, so I'll accept that the pressure, if I do this suggestion, I'm gonna suck at it, or I'm gonna breathe, I'm gonna expand this volume somehow. The pressure here is gonna drop. How is that gonna affect the water? It's not the water, the molecules which are inside the vessel, which I actually want to pump.
Different pressure from.
Sorry?
There's a different pressure from the other vessel.
Yeah.
That's the one at equilibrium, right? So.
Yeah, but let's assume that particles have their will and they really want to equilibrate and stuff like that. Okay, we love these words, we use them all the time. How do they know that this thing happens? Is it like a rumor? Guys, I've been told that there's a lot of space there. Please move there, okay?
I think that's it.
I just have a sixth sense.
Sixth sense, rumor. They
Well, is it-
Googled it up. How did they work out that the thing was expanding? Come on, seriously.
It's like they're bouncing in between anyway, and so when it's just a small, like on the right hand side, because there's a lot of molecules, the ones on the left are just going to bounce back in because they don't fit in that small section.
Mhm.
Like, 'cause there's not as much space.
Okay,
and when it opens
Okay,
up,
so
it's more
they're
space.
actually, the answer is there are two mechanisms. One, do you remember your name? Because Jack, I'm very bad with names, sorry, Jack. So Jack said that because they're moving randomly, they have some chance of going into this chamber, okay? And if there are less of them on the other side, you have less of the reverse process, right? So the pressure is going to equalize. That's very true, okay? It's also not very efficient. So it's going to happen. It's going to become more important in a bit, but it's not very efficient. But how can it be much more efficient if these guys could tell these guys, look, come over here. Don't just bounce randomly. Come to the right. Okay, random motion is okay, but it's not a great way to do things quickly. Okay, if you guys started walking around randomly, the room, eventually the room will be evacuated because once in a while, one of you would hit the door. That's it. He's gone because there's a big corridor there. Very few would be coming back. Okay, we could try this exercise as well. It's gonna be very interesting.
Let's do it.
Move the tables.
We can increase the temperature, so you'll be a bit more. We can do all kinds of. We can close half the door to amuse ourselves and stuff like that, right? Okay, so we could do it, and you'd be leaving the room, and Jack is absolutely right, but it's not very efficient. If I told you guys move this direction, that's where the door is, you'd be out of here in a second, right? That's it. And probably as soon as I told you the lesson's finished, you'd be out of here, right? Immediately. So So you need to transfer information. How do molecules transfer information?
Interaction.
Interactions. Now these are helium atoms. I forgot to tell you, just to make life more difficult. Very bad at interacting. Okay, they're
Very socially awkward.
yeah, socially awkward helium atoms. They think they're noble and no. Okay, so how do they interact? They still interact. It will work with helium atoms as well.
They collide.
They collide. Okay, so they collide. So if the idea is that basically interparticle collisions allow basically forces to be transferred, and this basically allows a directional flow towards a pump or towards low pressure, which in this case is the pump. Okay, so we're not just relying on random motion. We're doing something much more efficient. The particles are colliding. Because they're colliding more from the left to the right, and they're colliding right to the left, they're giving each other momentum, and they're collectively going to be evacuated pretty quickly. Okay. This is the basic idea. So if we but then again, there's a small problem here, because you said we would suck or I would somehow expand some volume, which would pump this guy, right? But there's a limit to how much I can expand my lungs, limit to how much you could suck on a straw. And so what do we do then? Come on, if we had to, we want to keep pumping it.
Two people.
And
Well, everyone has
COVID safe.
similar pressure.
You'd seal it. And then
Seal it, yeah. So basically that's why I connected this valve here. So in theory, we could close the valve, and these would be refill the empty, the thing which now has a depleted pressure with gas, open it up, there's going to be a suction power, okay? Okay, that is something that I think you would think about by yourselves if you were on this empty island. You just do it with your finger, not with a valve. Now this might or might not work. Probably not, because it might leak. Okay, so I need someone to actually close that valve when I expand so I'm gonna try to pull it. So this valve here, first see that you know how to open it and close it. You probably need two hands. You need one on the. Okay, so if you open it now, and if I reduce now, close. Okay, now, of course because there's a leak, it is losing the vacuum, but now open it again. Okay, and it is doing something, right? It's sort of doing it. Okay, that's the price of doing something without checking that it's leak proof. By the way, we're seeing the importance of leaks. Each time I close it, it was still, pressure was going up. Okay, that means I have a leak here somewhere. But this is a pump. Okay, this is a pump which I think costs probably 2-3 penny, whatever. Okay, you can get as many of those as you want, and it's a stupid way of pumping, but it will work. Okay. How do we pump something more efficiently than that? Of course, we automate it, we motorize it, or something like that. So let's look at the type of pump, which I think is probably. I mean, this specific specimen is a dead pump, but before it was dead, it was a working pump of a type called a piston pump. Now, sorry, this is not a piston. This is a diaphragm pump. Okay. Which I think you might have in your labs. Okay, it's usually just says pump and again an on button, but underneath it there's probably going to be a diaphragm pump, and you could later, I could move and you guys can look at the inside of these things, but essentially what you have here is it would be some kind of a polymer, so it'd be some kind of a flexible. In this case, not really flexible. Okay, there should be it's a semi-flexible thing, okay? Yeah, there's a flexible component here, and essentially what happens is that each time, this is actually a piston pump, not a, sorry, this is a piston pump, not a diaphragm pump, sorry, okay, because this is really rigid. So okay, so forget what I just said. Okay, you don't have to, I'll have to edit the recording later. this guy is a piston pump, where essentially what you have here is a thing here which goes up and down, okay? And there are two ways the gas can come out of this guy, either to the right chamber or to the left chamber, okay? And you have these one directional valves. So basically when gas is going in one way, it is pushing this piece of rubber out of the way, but when it won't go the other way because it's actually sealing. So there, you see this rubber here? So when the gas is pushed outwards, it can do what my finger is doing now, okay? When the gas wants to go this way, when the difference in pressure that way, it's sealing it. So these are like one directional valves. They go to two different chambers, and each time, so basically there's gas pushed out, gas pulled in, gas pushed out, gas pulled in. It's kind of the equivalent of what we try to do with this syringe. Okay, so this would be a piston pump. By the way, what you see about, one thing about these pumps is that what happens if you run them in reverse? Let's say you somehow replace the inlet and the outlet of these pumps. Sorry?
We'll just get blocked because they won't be able to go the other way to the valve.
Okay, so they block gas running away the wrong way. But let's say I somehow reverse their operational principle. So I put the valve which opens, and I reverse the directionality of this thing. That's called a compressor. Okay, that would just become a compressor. So it would basically extract gas and push it into a high pressure. Okay, so all these pumps, if you operate them in one directionality, they're compressors. You'd use them to fill air on your tire, whatever. If you reverse them, they become pumps. Okay, and this later, have a look at this thing. The idea is that you could use a principle which is called it's called a positive displacement. These are positive displacement pumps. Which basically kind of push and pull the gas by changing the volumes repeatedly. Okay, does this make sense? Now I might or might not be able to actually connect to that screen there. Let me try. Does this thing work sometimes? Have you?
Yeah, you can plug it.
There is a. I could try. Okay. So just to summarize what we just talked about. We were talking about positive displacement pumps. We basically saw 4 examples. The first one was the one okay, there was a stupid thing with the syringe, but that was just an idea. Okay, we saw the piston pump, which is the one I opened thinking it would be a diaphragm. We saw a diaphragm pump. We saw it's called rotary oil pump. And again, it's not important that you remember any of the details, just the basic idea. And a scroll pump. Typically, these 2 guys here, they can get down to basically the minimal pressure you can achieve. That's, again, I'm using very rough estimations here. The minimum pressure you're going to achieve is on the order of maybe 1 millibar if you're really lucky. Often much worse than that. It could be 10 millibar, something like that. And these guys could go down to a minimum temperature which is on the order of 10 to the -3 millibar. Okay, so that is 10 to the -6 of the bar, which is 1/1,000,000 of the pressure we live in our daily lives. Okay. So what stops these pumps from working after a while? So basically what limits these types of pumps?
Material limits.
Okay, so one of them is materials. So materials, for example, like oil, even though that actually achieves a better pressure, but never mind, are limited by PVAP, vapor pressure, which we talked about a lot. Okay, but there's also a more fundamental reason why these pumps would stop working. So they pump down, go down to 10 to the -3, and that's it. So can't do anything better than that. Sorry. You could use whatever oil. You could use an oil which has a vapor pressure of 10 to the -6. We have these oils, bloody expensive, pretty toxic, but they exist, and still the pump is not going to reach 10 to the -6. So if you had an idea of why they can't continue working, just from the knowledge that you already have from this course,
Do they get too hot?
they have water cooling, so they could get hot, and then of course the vapor pressure would go up, but they have water cooling to avoid that. What's the whole idea based on? So they had energy and motion and stuff, that's true, but we said that random motion was not really good enough for us, right? It's very ineffective. It has very low pumping speed. When again, we still might have to use that, but what makes them suddenly lose their efficiency a lot as the pressure goes down?
If we're relying on the particle collision, is there's less particles to collide when they're just like slow down the rate.
Exactly.
Actually, that
So
one?
exactly. So we said that we had we needed these particle collisions to pass the information or to pass the momentum from the high pressure to low pressure side. Okay. How do we know? And this is, you remember we've encountered something called the mean free path. Let's see if I could find a. Unfortunately, I don't have that with me, which is annoying. There's another page which I actually printed for you within Ring. Okay, so if you look, do you remember there was this concept we talked about, which was the mean free path? Do you remember the concept of mean free path? So we defined something which was lambda, which was the mean free path. What does that mean? Someone remind me what the mean free path means?
Average distance before collision takes place.
Exactly. So it's the average distance. For those of you who don't remember, maybe write it down. The average distance between collisions, or yeah. So it's some, of course, some will happen before, some will happen after. But this is and just to kind of, we had an equation to calculate it. Do you remember what it was? Or again, it's written there. It was, I think it was lambda. Maybe I have it written here. See, 1 over ND squared, something like that. 1 over root
2 pi d squared n prime.
Okay, the main thing here is this d squared, which was the dimension of the thing, right? And the n, which was, what was this n?
N prime is number of molecules over the volume.
Yeah. Okay, so this is n prime. Okay, so this was the number of molecules divided by the volume. So the density of the gas. Of course, the density, as the pressure goes down, what happens to the density? It goes down as well, right? That's the PV and KT. Right? There's so if you have, again, all the capabilities to calculate these things, but to save time, I'm going to just say it myself. If I look at a few of these values, so again, lambda, for example, at 1 atmosphere would be, if I did the calculation correctly, would be 66 nanometers. Okay. Not much. That would be 10 to the -9 of a meter. Could be wrong, but that's what it came up. If I take 1 millibar, I have 66 micrometers. Okay? If I now go for if I go to 10 to the minus, okay, So if I go to 10 to the minus 3 of a millibar, I have 66 millimeters. Okay. Now, the 66 is not important; just a number. It just happens to come out from that equation if you use it for nitrogen and so on. But and maybe just and yeah. And if I go to 10 to the minus 6 millibar, I would have 66 meters. Yeah. Okay. So this is not an exercise of multiplying by 1,000, though it looks like it, and learning all kinds of units. This actually tells you what's going to happen. So what's special about the this let's say the 10 to the minus 3 millibar region? We're talking about 60 something millimeters, which is about 6 centimeters, which is about that long. Okay. So what's special about that number? It's kind of the size of most of the things we have in our lab, right? So it's kind of the size of this vessel, which I wanted to pump. It's kind of the size, the distance between them. Again, tens of centimeters, 1 centimeter, 10 centimeter, doesn't matter, okay? What happens at these distances, the molecules are gonna bounce in between these walls pretty much at the same, they'll have the same chance of hitting from one wall, going from one wall to another without colliding as colliding. Okay, the collisions are become so rare, they could travel distances of centimeters without colliding. It suddenly means that the ability to transfer the forces is very limited. You're going to reach the door before someone tells you you should reach the door. Okay, and in this kind of a simple picture that we were looking at. Does that make sense? So basically, all these positive displacement pumps, and they work in what's called the continuum. What's the chance of writing that correctly? Continuum flow region. And the continuum flow region is defined as a region where the dimensions of the vessel are larger or much larger than lambda, which is the mean free path. So 10 to the minus 3 simply collisions are no longer efficient. So what limits these pumps? The number 2 is basically once a lambda is no longer much smaller than the typical dimensions of the vessel you're pumping, okay? And that basically kills these type of pumps. So at this point, we could say, okay, just let's limit pumping to 10 to the minus 3. That's it. That's what we could do. And that's fine for a lot of applications. But you remember when we were talking in one of the previous lessons, for a lot of applications, that's rubbish vacuum, okay? The amount of molecules which is going to contaminate your sample is huge. If you're trying to build a device in the semiconductor industry, you're going to end up with a horrible chip. If you work at these pressures, if you do surface chemistry, you can't do surface chemistry at these pressures. There's a lot of things you can do. There's a lot of things you can do, okay? So if you stick to organic chemistry, you can now leave the room and say, I don't want to hear about anything lower than that, okay? Or you could stay, just out of courtesy. But basically, it's probably going to be good enough for you, okay? You still need to understand, you know, when the different solvents are going to evaporate, but with your understanding of vapor pressure, you should be okay. You still need to choose the right pump for it to not catch fire when you're pumping your solvent, okay, for example, or disintegrate, or just pump badly, okay? but these are all technical issues which you'll figure out. But let's say you do want to go beyond 10 to the minus 3. You work in the industry and it's a very clean process, or you work in a lab which actually cares about these contaminations. And the question is, how do you do it? So how do you pump below? How do you pump when basically collisions are no longer efficient? When this guy is no longer happening?
Increase temperature.
You can increase the temperature. What's that going to do?
We're just going to have to deal with
More collisions.
the vapor.
Yeah, actually, if you remember if we look at this guy here, there's nothing here which is temperature dependent, right? Because there's a density, which is what it is. It's just a function of pressure and volume. Okay, I mean you could change it a little bit, but it's not gonna affect your lambda much. So it might be that it might slightly increase your pumping speed, but then again you'll go down to 10 to the minus 4 and you have no collisions. Well, what can you do?
Smaller volume.
What's that?
Smaller volume.
Smaller volume. Not really. So it's still a fundamental limit here because. Okay, so sorry. So what's going to happen, regardless if the volume is small? I mean, let's go back, because some of you, unfortunately for me, already picked up on the idea of how it's going to work before we enter this other regime. Because if this is our pump here, and this is the vessel that we want to actually pump out, and you said correctly that random motion is still going to direct molecules toward the pump. Okay, so we said it's not efficient. We're very patient people. We'll just wait for the molecules to arrive to that point. Okay, so the molecules will at some point reach the pump. What do we need in order for that device to actually pump? What's this? So we can rely on random motion. We have to rely on random motion is the answer. But is that enough? The molecules come to the pump and they say, oh, this is not better than the vessel I came in. I'm going to keep randomly moving, even though it's called a pump, but the label pump is on the outside of the vessel, so they don't see it's a pump. From their point of view, it's just another volume. They might have a chance of going all the way back. Okay. Oh, I'm back. Okay.
The other vessel.
What's that?
You pump the other vessel.
But with what? If it has the same pressure, again, we're stuck, right?
In the opposite way.
You can calculate the third vessel and the fourth vessel and the fifth, we'll already forget that the problem exists and it will work. What do I need to do? It's true, I need to reduce the pressure in the pump. But how can I reduce the pressure in the pump?
Make the pump colder.
Colder would be an interesting idea. Okay, that's called the Kraft. That actually there is a pump which works like that. But so the idea is maybe let's write it down a bit. Let's write some of your ideas here. Can I erase this?
Yeah.
Okay. So basically, in order to pump, basically to pressures which are kind of smaller than 10 to the minus 3 millibars, and that's the unit that I happen to like. You need pumps which work in something which is called the molecular flow regime. The molecular flow regime is where the lambda is much bigger than d. This is the mean free path, and this is the kind of size of a vessel. So this is the opposite regime. If before lambda was much smaller, so we had an atmosphere, we had 66 nanometers before a molecule collided with another molecule. Okay, that was much smaller than the typical sizes. That stopped at 10 to the minus 3, and then we need to go into this molecular flow regime. And in order to do that, you basically need to rely on random motion to reach the pump. And And then basically your second stage is you need to somehow extract the molecules or the atoms from the pump. Or you could alternatively, I think the phrase was kill them dead. Okay, somehow. It's actually not a joke. You kill particles. We should see it. Okay. Somehow. So, how are we doing with time? Yeah, not that great. Okay. Are you good to go for another 10 minutes or so? Okay. If it becomes like, it's coming on in from one ear and going on from the other, then you have to stop. So let's think about the first thing, which is relying on random motion to reach the pump. Okay. And then we'll talk about extracting molecules from the pump, or maybe killing them dead, probably in the beginning of next lesson. I want to, in order to understand that, basically to understand one, so this is this random motion. Let's think about, let's look at the effect of one of the things would be the pump inlet size, and two, it would be the length and the diameters of the tubes. Okay, I'll explain what I mean by that. Let's start with the first one is obvious, okay? It's obvious to you guys because you guys took this course and you know the single most important concept in this course is impingement rate, okay? It's the answer to almost everything. So if I have a vessel here and I have a pump here, okay, this is the connection to the pump. And this is my vessel. I'm relying on random motion. So if I have this small entrance to the pump, how is that going to affect the ability to remove particles if it's based on random motion?
It will be small. There's not much space for it.
Yeah, because you remember that the impingement rate, so basically the number of molecules reaching the pump will be the impingement flux, right, J, multiplied by area. This is the surface area of inlet, okay, of the pump, the inlet of the pump. Do we agree on that? If I'm going to make it very small, it's like this door. I'm going to make a very small door, and you guys are going to move randomly. There's going to be less pumping through the door. Okay, if I pick a bigger one, okay. So that's kind of obvious, right? So when we'll the last lesson we'll go down and see some pumps, which are a bit more sophisticated than this guy, which I disassembled here. Then basically we'll see the big ones. They're the ones which can pump a lot of gas if you're relying on random motion. Okay. We didn't have this problem when we were at the opposite side of lambda and d here, where lambda was very small and forces, we could lure the particles into that small door. Okay, we could push them around and they would go through a small door. That doesn't happen when they're moving randomly, it reduces, okay? So that's the first thing. The second thing is the effect of the length and diameter of the tubes connecting it. So let's concentrate for a second on this tube here, which is connecting the pump to the rest of the vessel. And there is something, have you ever, you probably didn't hear, there's something called the Knudsen cosine law. Has anyone ever heard about the Knudsen cosine law?
No.
Okay, fair enough. This is celebrity and some other, century, when scientists were celebrities. Knudsen cosine law tells you, it tells you that basically particles, that could be molecules or atom, scatter, and I'll explain what that means, scatter from surfaces following a cosine distribution. You do know what a cosine is, right? Say yes, even if you don't, okay?
Yeah.
Thank you. Come on, you do. Cosine signs, we could remind you of that. But all these markers. Read them off. Okay. Do some of you play squash? You've ever played squash? Ping pong or tennis? All good examples. Or if not, have seen it, have watched TV and seen someone hit balls at crazy and kind of velocities towards walls and stuff, right? Yes. So that's not going to help you at all, okay? Because Knudsen law tells you that particles don't behave like that, okay? So when we have, if this is our surface, if this is our surface and this molecule N2, which is the common molecule of this air around us, hits the wall, it is not a squash ball, it's not a tennis ball, it's not a ping pong ball. Because if it were, when it would hit the surface, we'd say, oh, we know where it's going. If this angle here is theta, it's gonna be angle in, okay, it didn't come out in the drawing, angle in equals angle out, this is also theta, and I'm gonna find the molecule here, okay? If the molecules would behave like squash balls or tennis balls, whatever, it's all built on that, right? So the tennis player sees with his eyes where it's hitting the floor. He already knows because he does these calculations and he could do all kinds of trigonometry calculations quickly, and then he knows where to put his racket because he knows it doesn't work, okay? Why does it not work with molecules hitting walls?
Funny shapes.
What's that?
The different shapes. Yeah.
Again?
The shapes of the molecule.
The shape of what the molecule might, okay, so, okay, let's replace it with helium atoms, okay? Here comes the helium atom, it's always there to annoy. Each time we put some interaction, there comes the helium atom, it's spherical, inert.
Is it because they're not affected by gravity?
Because they're what, right?
Not affected by gravity.
Gravity would complicate things, but you could play squash in space. It's not, you just take, if the ball goes off, it goes off, right? But basically, other than that situation, the angle of the coming in is going to be the angle of the incident angle be equal to. What else is different on these scales of atoms and molecules?
Well, the size of, like, the comparison, like a ball to a wall, if there's like a bump in the surface of the wall.
Well, what's a wall anyway? Atoms, right?
Yeah.
So it's about scales. So first of all, the wall doesn't look like this. If the particle, if that's the scale of the particle, then the wall is not flat, right? The wall has ions and has a sea of electrons, which surrounds these atoms. And it's not going to be flat because it's not the same electron density near an ion and further away from an ion, okay? That's even if the surface was perfect. Then come defects, then come adsorbed molecules. Life becomes more and more and more tricky. Then to make things more annoying, the atom or the molecule has a chance to stick and then desorb. Who says it's going to come out with the same energy? Who says it's going to come out immediately? So you have all these processes. They're called inelastic scattering, adsorption, desorption, lots of things happening, okay? So the model of the ball in the wall doesn't hold for atoms and molecules with surfaces generally. It could under very, very specific situations, you might get that, but generally it's not what you get. And what Knudsen's law tells us, it tells us that basically, if I drew a graph of the probability of, let's say, finding a scattered particle, scattered or you can think about scattered or ejected particle, okay? And the horizontal scale was theta, which is the same theta I drew before. And basically what Knudsen's law tells us, it tells us that it's basically a cosine. So a cosine has its maximum value at 0. Okay, when does cosine actually go to 0? At 90 degrees, cosine becomes 0. Okay, so this would be 90 degrees. This would be 0 degrees. This would be minus 90 degrees. Okay, a cosine would continue oscillating, but we're only interested in the first. So what it tells you that the molecules, when they eject from here, they have a certain probability of flying that way, certain probability of flying that way, and so on. But they have the largest probability of actually being ejected upwards. Okay? And they have a 0 probability of going exactly horizontal, running along the surface. And in between, it increases like the cosine. Okay, that's called Knudsen law. Okay, it's an experimental observation. It's impossible to find a model which gives that result, but it's an experimental observation which kind of works. So first of all, why is that an issue for particles which are trying to reach the pump? In the molecular flow regime, do they collide more with each other or collide more with the walls? More with the walls, because lambda is so big. We're going to 10 to the minus 6. Lambda is 66 meters. It's going to hit the walls lots and lots of times before it ever hits another particle. Okay? So now let's think about the poor particle which is trying to reach the pump through some kind of a tube. Okay? So it comes, so first of all, this is my vessel. What was the velocity of the particle for it to go there in the first place? If it was moving this way, is it going to reach the pump? No, right? So it has to wait for a bit, it bounces, and then, oh, great. Now I'm going inwards. Yay, I'm going towards the pump, okay? It arrives, but if it's not moving exactly in a straight line or within a certain range of angles, it's going to hit the wall, right? What happens when it hits the wall? It has to decide, am I playing squash or do I know Knudsen's rule? If I'm playing squash, game over. Chick, 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 into the pump, okay? But that's not what's happening. What's happening is Knudsen law. So what's the most probable direction it's going to be ejected?
Anywhere.
That way, that way, that way, and a little bit backwards, okay? So that is really demoralizing, right? You're on your way to the pump, and basically it's forgotten that you had this correct trajectory, and now you have a 50% chance of going left and right, okay? So you still have a chance of going forward, but you have an equal chance of going backwards just because you hit the wall, okay? Okay, so you're going that way, okay? Now you hit the wall again. Against all odds, you were moving to the right direction, but again, you have a 50-50 chance of going right or left. So you're losing a lot of molecules here which are bouncing that way. But then you have some which are going that way, okay, and so on and so forth. That reduces, so the longer the tube is, or the thinner the tube is, the less pumping you have, okay? So if you want to make a molecular flow pump efficient, you want to have a big opening and a short tube connecting it to where you kill the molecules somehow or extract them, okay? Does that make sense? And this is something which you cannot use your intuition to understand. So Knudsen law, you have to actually bounce molecules off surfaces to work it out. Okay, our intuition tells us that if we're going from left to right, we're going to remember that, and chance of going further to the right it's not what happens. Okay, in general. Right. So I don't want to push the limits here. So in the next and last lesson, what we're going to do is we're going to talk a little bit about once these fortunate particles made it to the pump, how do we actually extract them? It's not going to take long. We're going to meet 2 or 3 pumps which are good at doing that. We're going to talk just a little bit about how you measure pressures. And then we're going to go down to the lab and just try to see with our eyes how these various components look like, and pretty much that's it. Okay? So I'll see you tomorrow at the same time.